So or at least I would like to go there, and I'll show you how I would like to go there, but we're not there yet. So what we're going to discuss today is really manifold learning, or an attempt to do really manifold reduction. And then the learning should come on top. And this is part of the thesis that Fabrizio did at Georgia Tech, and he's now here, and he's a postdoc with Laura. And we have worked a lot with complex network and entropy. And what we have been trying to do is really to mix dynamical system theory with data science methods, essentially, and large data science methods. And this is just one example, and I hope that there is something that could be used. I'm going to talk about ENSO. Hank has given a talk on that, so I'm hoping that you all know what ENSO is at this point. And I'm going to focus on the Pacific, and especially in this area from here to here pretty much. And if you're not a climate scientist, the only thing you need to realize here is that we have on average the largest sea surface temperature that we have on the planet. So we also have a lot of convection. And we have an area here, which is the cold tongue, where instead you have upwelling and you bring to the surface relatively cold water. And this kind of pattern can change interannually depending on in which phase of the El Niño-Sadr oscillation you are. The three phases are here. And what really changes the distribution of the sea surface temperature, the distribution of the thermocline, and the water circulation on top of it. So you go from normal or neutral conditions where you have most of the deconvection in the warm pool and subsidence in the cold tongue, to a condition where you are completely shifted the convection in the central Pacific, and really change the distribution of your clouds, of course, and the distribution of the winds and the distribution of the sea surface temperature. And you kind of get the opposite with a strengthening of the convection area and a pileup of very warm water during La Nina condition in the warm pool. Why do we care about ENSO? This is also something that Hank kind of mentioned. And this is just a time series of the Niño 3.4 index for reference from the 1950, I believe. It is teleconnected pretty much everywhere. And so if you're looking about climate and climate change, you want to know what ENSO is going to do in the future, because it's going to kind of change what your variability is going to be pretty much everywhere in terms of precipitation, in terms of tropical storm, marine heat waves. You know, in El Niño and La Nina really determines how bad is going to be your hurricane season in the Atlantic, on top of what is going to be in the Pacific. Connectivity with the basin, with the Indian Ocean, huge ecosystem impacts around here. Every time you hear about corals dying, that's pretty much because there is an El Niño somewhere, and it's a strong one. So mass extinctions of corals all in this area have been associated with El Niño. So we would like to know what happened in the future, right? Because if it's going to get stronger and more often, it's going to be a problem, and it's going to be different than going into a permanent La Nina condition, for example, as has been said in the past. So this is again just a plot to also show you all it's connected to Kelvin waves and Rossby wave in the atmosphere pretty much everywhere. And so if you modify what the circulation, the atmospheric circulation is in this region, you're kind of going to impact everywhere. So what do models say about it? Everything and more. So this is a first look, and Anish was involved in this work in the CIMIP 6. And it doesn't really matter what those figures are saying, except that what you can see is that those are all different models. And the only thing that is important here is that those things are going up or going down. And there is no agreement in the CIMIP 6 models of where those bars are going, in terms of sign, at least. You can find McFadden saying in 2020 that almost for sure extreme El Niño and La Niñas are going to become more common with global warming. So we are going to probably have one every 10 years instead of one every 20. And then you can find one of the nature, I think is nature climate change this here, saying no, that's absolutely the opposite. We are going to have an increase in very strong decrease in variability in ENSO, and so the ENSO is just going to become weaker. And the reason nobody understood that before is that the models are too coarse. So once you increase the resolution of the model, that's where you get. Of course, they're looking at one model. So honestly, I don't remember. Is CSM? It doesn't really matter. I can show you, I'm going to show you another one where the opposite happened and it's a high resolution too. So just as a spoiler, it doesn't matter. So, you know, we would like to know what's going to happen. And we would like to know what is going to happen on a lot of other things, but this is one that is relatively simple because it's been incredibly well studied. If you remember some of the plots, and I should have put another one, a different one that Laura showed at the beginning, the Pacific is still one of those places where the climatology more or less agree. If you go to high latitudes, those models do anything and more. But in the Pacific, at least in terms of climatology, they are doing relatively well for the historical period. So you would hope that they could agree a little bit more on the variability. The answer is not. We're trying to figure it out why. So we start from a system that is complex, multidimensional, multiscale, is nonlinear. We have a huge amount of variables, and we have relatively few observations. And we're kind of lucky in the Pacific. Again, we do have a relatively decent system of observation compared to other places. So what we can do? Well, we can at least use the fact that the system is distributive. And there has been very nice work done by Lucarini in the last few years. This is a book, I think Lucarini et al. From 2016. I should put the et al. There, which it, you know, kind of show you kind of convincingly it's true, it's high dimensional, but it's distributive. And so if you look at the dynamics, you do expect to have them confined on a manifold that has a relatively small number of degree of freedom, at least to compare to the full space. Okay. So the dimensionality of the manifold of the system is not as big as the whole system because of that distributive component. So can we try to reduce that dimensionality? Yes, we usually do that a lot in climate science. We use UF or PCA. Can we use something different? We can try to do something that is a little bit less constrained to linear processes or linear distances, Euclidean distances. So we can use, for example, Isomath, which is one of the nonlinear algorithms that is going to look at different kinds of distances. So what we do here is to take ERA 5 as proxy for truth and history analysis. So there is some modeling component in that as well, but it's as good as we can do if we want to look at a long enough period. We take 40 years and we take two models, MPI and EC-Earth. We are looking at 79 2019, and then we are also looking at the SSP 585 scenario from 2060 to 2100 in the model. The last 4 years here in the models are also from the same scenario. We are using daily data. So that's a lot of data. And we are focusing only on the Pacific, the tropical Pacific. Again, this was a proof of concept. You can do it everywhere. You can do it globally. And we're going to use 5 variables. And you can use 20, but we are going to focus on 5 because, again, this was a proof of concept. And we're going to look at SST, winds at near the surface, 925, U and V, OLR, and sea surface temperature. We probably should have put also the ocean thermoclines that we were getting in another problem we needed a different reanalysis and we needed a different grid. And so we just try to simplify things, but it's, you know, again, this was a proof of concept. So, okay, this is just a quick description of the models. And I want to stress simply the fact that they are different. They have different modules. This was when we started this project. This is pretty much what was available at daily resolution for the 40 years we were looking at. The nice thing about this Earth is that it's high resolution compared to most of the traditional symmetrics, because it's at a quarter of a degree in the ocean and is at about 40 kilometers. It's a T511 spectral resolution in the atmosphere, use IFS. The other good things is that this is the MCNWF model, which is consistent with the ERA5. At least you would expect, or you would hope that there is some consistency between those two, right? Because it's the same group that is generating the reanalysis. And again, it's 40 kilometers. It's you know, pretty good, both in the atmosphere and in the ocean. And those are all the components. The other one, it's more traditional, 0.4 for the ocean and 1 degree in the atmosphere. We are going to downscale everything to 1 degree because otherwise we cannot do the comparison, right? So we're going to have 1 degree everywhere, but we start from the outcome of that. So what are the steps? We are going to take those 5 variables, as I mentioned, and we are going to build a high dimensional trajectory in time that has the dimensionality of R to the Tn, where n is the dimensional trajectory, 17,000 about, and time is 14,000 days. And then we're going to look for the manifold, linear, and using Isomath. And we are going to try to visualize it, and we have to do with 3D because that's pretty much how we can visualize things relatively easily. We cannot do it much higher dimension than that. And by doing both, we can actually also see how the linear component versus the nonlinear component matters, and we can compare that in the data, in the analysis and in the model. And we can then try to estimate some of the characteristics of the manifold in the observations and in the model using metrics that have been developed by the Lucarin's group and Faranda. And there is a nice paper in Scientific Report in 2017. And we are going specifically to use 2 metrics. One is the local dimension, and the other is actually the inverse of the average persistence. And I'm going to show you next what those 2 properties to kind of quantify manifold are. So this is the well-known. Okay? So we're looking at Lorentz. And if we want to look at the local dimension, what we're going to quantify is essentially based on this theorem, the quantity that you see here. And the theorem has been proved for chaotic system. And what this is giving you is the dimensionality of this attractor at each point of the attractor. If you take the average of that, the dimensionality should be the dimensionality of the Lorentz attractor, which is 2.06. And it turns out that that's correct. And it gives you the correct answer. If you want to look what the map of a local dimension looks like for Lorentz, this is what it looks like. Whenever you have a stable point, you have a very low dimension. A fixed point is dimension 0, essentially. Whenever you are away from the fixed points in the divergence part of the trajectory, you're going to have a very high dimension, local dimension. And whenever you are in the areas that are subsampled by the attractor, you're also going to have a high dimension. So in a way, this is a measure of how complex or chaotic is your state in at that point in time. Okay. So we can do the same and look at instead at the persistent or local stability. So what you do is that you take a state, you set a threshold that defines a neighbor of that state, and you look at how occupied, how busy is the neighbor of that state defined by that threshold. And that is essentially define the persistency or the inverse of a persistency. So it's the inverse of the average time spent above U in this case, but it's essentially how much time your system is going to spend around that state. And again, if you look at Lorentz, once you are at the center, you have steady state, so you're going to be there as much as you want, essentially. When you are out here, you're going to stay there for very little time, and you're just going to escape very quickly, so your inverse of persistency is high. And when that happens, I mean, the other thing that you can see kind of visually, just looking at this, and this one is that there is some relation between the two, are not exactly the same, but you can also look for things like points that have, or states, because this is in phase space, states that have very high persistency and very low dimension, for example, and vice versa. Okay, so you can go in the high and the low and see what is in the middle and try to characterize your manifold. So what happens if we do something like that on a climate model output, and if we build this around 5 variables? So our state space is with its multivariable, and you know we can imagine using 20. Okay, so this is what happened taking the raw data. So this is include the seasonal cycle. So what what comes out is going to be a donut, because you do have a seasonal cycle. The nice thing here is that you can see that there is some difference. I mean, if you plot it, this is in 3 dimension, you can kind of see that the blues was under the yellow. So essentially you are slightly changing the seasonal cycle with warming over the last 40 years. There is a trend. It's hard to visualize, but there is a little bit of trend there. And there is both in the model and the observations. And again, the observation is 0.5. So the other thing that you see, this is by the way, this is the Isomath projection. Okay, so those are the first 2 components of Isomath. This is 1, 2, and 3. Okay. The other thing that you can see is that for the 2 models, there is kind of a very nice shaped donut. While for era 5, there are some points that are outside the donuts. And if you actually look at what those points are, those are the 2 bigger linears. This is the 96. Here are the years are colored in base of the time, so the day that they were. And what you find is that one is the 83 and the other is the 96 event. And the little yellowish that comes out here, this is the 2015. Lastly, you can look at the residual variance. With Isomath, you cannot calculate. You don't get the explained variance, but you can get the residual. So the residual variance in Isomath for each component is the black line, and the one for PCA it's the black dots, and the empty dots, the circles, are the one for PCA. And what you can see is that there is also in the seasonal cycle some nonlinearity, but it's not too much. And overall, the models are not doing too badly. Interesting, they are actually doing worse in SSTs than they are in the other variables. Okay. Then what you can do is that you can take those components and project them on the various fields and see what the pattern is, not just the variability, but also the spatial pattern. This is the variability. Okay, so it's the seasonal cycle. I mean, we are just kind of trying. And those are the patterns in era 5. If you project that component, the first component on each of the fields that we are considering, those are the difference between the model, the era 5, and the era 5 projection minus model projection. We have kind of learned to do temperature. So we are doing better there. Not surprisingly, we are not doing well in OLR. We are not doing great on the winds as well. I mean, the error is half of the sigma in the projections. It's not great for sure, both in U and V, by the way. But definitely here, we're actually, MPI is actually doing a little better than EC Earth, despite the resolution. And also, as you can expect, low-level clouds, complete mess. Both here and here. Yeah.
What's plotted here for T is 2-meter temperature, and it's an anomaly?
This is essentially is the regression of your principal component on the temperature.
Okay, so the Isomath first component.
Yeah.
Thanks.
And of course, it's just a seasonal cycle, right?
Right.
I mean, it's the whole signal, so you're going to see the seasonal cycle. We can remove the seasonal cycle, and we can look at the anomalies, and this is what happened. And this gets a little bit more interesting, I think. First of all, now PCA and Isomath, they're really quite different. And you actually do a much better job using Isomath, and the first 4 or 5 components of Isomath kind of explain 80%, or at a residual variance of about 20%, to be precise. Well, if you use PCAs, you have definitely much more. You're up, you're up to 60, 50. And that's a big difference. It's not true for the models. The models don't have the same amount of nonlinearity that the reanalysis has, for sure. The other thing is that if you look at the attractor or the manifold, again 2D and 3D, you have a clear kind of second wing in era 5 that you completely missed in the 2 models. And it's one run, it's 40 years. We may be missing some events, some extreme events, but definitely there is a different distribution that you can see. I mean, you would expect to at least feel the same space on the manifold, and clearly we are not doing it. Okay. And again, this is colored by the year. So what you see in this space, in this piece of the space, are the 3 big events. Those are the 3 large El Niños. We can quantify at this point the Euclidean distance versus the Joy.
Can I ask a question?
Yeah,
about previous slide? So,
of course.
like for MPI, there is a grand ensemble with like 100 members.
Yes.
So have you looked at the members to see maybe some of them?
No, not yet. We looked at ECR. Yeah.
Okay. But CS and the lens.
So Fabrizio looked at least another member on which we have control on ECR, and the thing was the same, but it was for this one. Okay, we have not. I mean, this needs to be done on a large ensemble, but developing the tools was already the big part of this thing, because again, we are using 5 variables at the same time, right? So it gets we have to figure it out how things are going first. And this is just a quantification of the nonlinearity in the 3 data set in terms of distance, and the fact that actually ECR is the one that is underestimating the nonlinearity more than MPI, despite the high resolution, which to me was surprising. And because it's a relatively large difference, at least in the atmosphere, in terms of the resolution of the 2 models. So this is the first Isomath component, the time series for the model and for the era 5 and for the models. And I think that PCI is in blue is Isomath, and in orange on the top is PCA. So of course the first is still very similar, and it's very highly correlated with an Enfield index. If you take Niño 3.4, you're going to find a high correlation with that. In the observation, you can see the power spectrum. We can calculate the power spectrum in the 2 models. MPI is a little bit off. It's a very strong peak at about 8 years. Kind of large oscillation compared to what is in the reanalysis. ECR is doing better. ECR has been tuned, and I don't know what they did to tune it, because there is a previous article where they actually checked that this model was having, this is kind of interesting to me as a modeler, this model was having an 8-year kind of regular El Niño ENSO cycle. And they added stochastic physics, and that problem went away. But this does not have stochastic physics. So the one that they deposited and that they ran for the SIMI 5, so this was tested done 3 years ago, so 4 years ago, What had been deposited in CIMI5 still has a perfect spectrum, very nice. Right peak, I mean, very, very nice. But the moment you let it go on its own, it goes here. So this is the last frontier of the 2100. It's perfect 8-year like that. Right? So it gets extremely irregular. Well, MPI doesn't change much. MPI already in the previous version in CIMI6 was one of the most stable models that you could find, and it remains in this new version. What you see here is the projection of the first Isomath component on the various fields again. And what you can see is also how they are essentially reproducing the temperature or OLR anomalies associated with El Niño in the analysis and in the various models, so you can have an idea of where the errors are. Clearly, OLR, it's a little bit of a problem. You still have the double ATCZ here, but definitely also U and V have some problem, and the SSD is usually too much confined at the equator in EC Earth and too much weight in the Central Pacific in MPI. You go into the future, EC Earth goes in this really strong regular cycle of ENSO, and this is the very strongly correlated the SSD with the OLR at that point. So what you can do is to take this multivariable time series that you have and see how they are the first Isomath component for each variable, it's correlated with the multivariable case. And that is giving you an idea of how much you have in terms of how each variable is contributed to the signal, essentially, and how that is going to change. Era 5 is up here, so the temperature it's up there. I mean, it's the one that explains most of the signal because it's essentially an ENSO index, so that's not surprising. Of course, you can do this for the second component and the third, which would be quite interesting to see. We have done it on a simpler case on looking at the second and third component, but not on this one. There is an underestimation for U. They're not doing too badly for V. They're not doing too badly for OLR, present time. In the future, what really changes in EC Earth is U. So the zonal winds suddenly becomes really strongly correlated with what the SSTs are doing, which was not the case at all. In fact, it was underestimating the observations before. And it goes up here. V, it's even less. This is today in the reanalysis. But U really goes, it's, you know, 0.8 correlated with the SSTs, which is kind of a little bit unrealistic. And then quite stronger correlation with OLR. This was obvious from the maps. We can look at what the measurements are. Well, I will go 3 minutes over time. I can use, I had some questions. In terms of, this is ENSO. So you are seeing, we are coloring by the ENSO index, the distance and the inverse of persistency. So obviously El Niño, strong El Niño is persistent and it's relatively regular. So it's semi-stable. So you're going to see here. You actually can see the asymmetry between El Niño and La Niña here pretty well in this metric. MPI messes up completely. It does better in the future in terms of being similar to the observation. EC Earth is kind of mess all around. So the El Niño, the ENSO cycle does not have the property of the quasi-stable oscillator that should have in nature, essentially. And the nonlinearities are still quite wrong. And you can kind of see it nicely with these measurements. But the problem is also the large amount of points that you have here, and to appreciate how big it is, those are the PDFs. So those are the PDFs in local dimension and inverse of persistency for ERA and for the model. the nice thing that what really I was surprised to see are identical almost for the models today. And I'm willing to bet that almost any model will give you the same distribution. In those two models are almost as different as I can think of. And they are still giving you exactly the same, underestimating the tails, completely underestimating the kurtosis and the mean of the PDF. And the same is true for the inverse of persistency, even if it's a little bit better. And then in the future, they change in a completely different way with MPI not changing at all. This is just a different way of coloring by the properties the attractor. And here you can also see just visually how different are the models from year 5. It's a really nice visualization of those differences. So I'm coming to the conclusions, and you know, we seem to essentially underestimate the chaoticity of the system quite a lot. It's kind of expected. What the next obvious step is to take a stochastic parameterized model, a model with stochastic parameterization, and see if you shift. I don't think, but maybe. We still have this problem of having different answer representation in the future despite close representation today, and it really seems to be linked at how surface fields are responding to SST changes, essentially. And then, I mean, we do have the residual variance for Isomath in year 5 is very different in terms of variability from what we find in the model. So the nonlinearity in the model is really not captured properly. What we want to do next, I'm just going to go here. This is our idea. So we want to couple that manifold learning with a graph-based deep learning system. So what we want to do is to take a recurrent graph network, which has a casual message passing, and make it learn the interrelation between the variables so that we can try to facilitate prediction. Then we want to adopt the radial basing function encoding for spatial encoding in the RGM to kind of try to get to the regional and global spatial temporal relationship, and then constrain the RGM to learn the phase space manifold from the reanalysis to see if we can figure it out how that manifold is changing over time and try to project it in the future. And all this is with Saibal, and I'm not going to say his last name because I will not say it properly, which is in computer engineering at Georgia Tech. And this is the nice schematic that he put together to explain all of that, of which, of course, I understand 1/5 of it. But I mean, we're hoping to get there. We're now very excited to try out. So that's it. Thank you.
Go ahead. Yeah, Judith, sorry.
Hi, hello. Thank you very much. Very interesting talk. I think I would need to hear it again to fully understand what you're doing. I have two comments, which are really based on my interest or rooted in my interest. So one of them was that you were wondering why ENSO becomes nonlinear. So I work on stochastic parameterizations, and we have looked in the CSM model, which is the NCAR climate model, a state-of-the-art climate model, how the stochastic parameterization change ENSO regularity. And I think I understand that. I think it doesn't have to be stochasticity. I think it can just be mesoscale and weather variability. So if you're interested in this, I'm very happy to point you to a paper. It's done at 2019. I think I really understand the dynamical processes rather than the physics of it. So what do you need? And it's fluctuations of some kind. The other thing is I've done a long time ago some work. And so I think that's why I'm saying I might not fully understand your talk, what you really want to do with the isomaths. Are you trying to look into a reduced state parameterization, phase space representation, or are you trying to look at the nonlinearity? Because what we found is we were having a million years of no, million days of winter data from a GCM RUM, and we were looking for nonlinearity in this. It was geopotential height, but we were looking for nonlinearity in the model. And if we ask the question, where is the model going to be 12 hours later, then the dominating signal is climatology. You will always move to climatology. But if you ask where you're going to be in 30 minutes, we got a very different picture. And in this case, which was sort of Z500, we got a blocked and a zonal state, and it looked very much like some simple models that have been done that have been showing that blocked and zonal states in Z500 are really important. And frankly, it looked like the Lorentz detector. But if we said where I'm going to be in 12 hours, we could not see that nonlinearity because it was so masked by linearity. And so depending on what you want, and it's a bit like the seasonal cycle, right? If you keep the seasonal cycle in, you're very good at representing because models do that, and they don't do it always, right? I understand, but that's much easier to capture by a model or by a neural network. And so if you really want to make, so for example, a subseasonal prediction, you have to remove the seasonal cycle because otherwise you think you're going to make a perfect forecast because you did forecast the seasonal cycle. And so so these are just some comments, and how they fit in on what you really want to do is not totally clear to me how relevant they are. Thank you so much.
So on the first one, that comment about how they got rid of, that's really just a paper that was published on ECEarth, where they were complaining about this 8-year periodicity in the historical run. And they put a stochastic parameterization, it went away. And then they submitted those runs that don't have the stochastic parameterization, don't have the periodicity problem anymore. But as soon as you let run the model in the future, the periodicity problem comes back. So there is something in the tuning of that model. So that was all my comments. Okay, that has been done to correct that problem, but it's clearly not been done to a level that will continue in the future. As soon as the model is free, it goes back to that problem. In terms of what we want to do with Isomath, for us is really a way to reduce the dimensionality of the problem and to be able to see to a smaller, to a system which is reduced essentially, and try to look at what the properties are. I do understand the fact that at the end of the game, what I need is the climatology. I mean, if I want to do climate, but the problem is that those models have a very similar climatology and are doing a very different answer in the future. So there is some feedback and some linearities in those models that is different across the models, right? Because otherwise they would all have the same answer, at least given how closer they are to each other in a present time in their simulations compared to where they go in the future. And the fact that what I may need is only the average dimension of the actual manifold of my system, because that's really what matters. But I don't think the models are still really quite off. It's not just that they are underestimating the extreme, right? I mean, they are completely underestimating the average dimension of that attractor. And so I don't think that they can, I personally don't trust a projection that it's trying to get me to a future answer of what the climate is going to look in terms of its variability, if I'm not at least capturing the average dimension of the dynamical system.
Should we also go to some of the other questions, perhaps?
Sure.
Hey, it's really fascinating work. And this is a really nice method. If you go a few slides forward, so where you show the PDF of theta and D, yeah, here.
Yeah.
So there is like the first, in the first row, the two models have similar theta and D, right?
Yeah.
PDF. But then in the second row, the D is the same, for theta is different. And theta and D have different interpretations. So
yeah.
does that tell you something about the physics of what's missing? Because one is related to the stability of a trajectory.
Yes.
And the other one is the degrees of freedom. So does this difference tell you something?
Well, I mean, what it's telling me is that easier. It is going in this very stable ENSO, which is going to bring up this tail, right?
Sure.
So this is the result of having a cycle on a very regular, not enough chaotic ENSO that is changing like that. It's not changing dramatically in how the system it's doing the local dimension. And this is, again, is telling me that from here to here, there has been quite a bit of tuning so that you didn't see that problem here, but
okay.
it should have been there as well.
Okay. But can that be used to figure out where the model bias is? Anyway, just a question because
I don't know if I would rather use this one. This to me is more informative. This is telling me which kind of relation between variables is changing dramatically between past and future, and where the model is wrong compared to the observations to begin with.
Okay.
So this would be my first guess if I want to look at where the models are wrong. And of course, again, this is a 5-variable system, and you know, you would have to include more, but at that point, we know how to do it.
thanks.
Hi, thanks for the talk. I think it's a great idea to turn to nonlinear dimensionality reduction. And the message I got from your talk is that it did better than PCA. I do want to make you aware of an entire literature on nonlinear dimensionality reduction. You could even just kernelize your PCA. And I think the picture from your CS collaborator might be a little over the top. I mean, the first things I would try, in addition to kernelize PCA with different kernels, would be techniques in the non-deep learning literature, like random projection trees. But even in the deep learning literature, that's the whole idea of doing an autoencoder, or if you want a distribution over your embeddings, doing a variational autoencoder or a normalizing flow. And then they're also starting to be these unsupervised deep learning methods using contrastive losses, where you just need to train by saying these kinds of data points are similar and these are different. So anyway, let's talk about it while you're here, because
yes.
I think you could do something. So first you have to see which dimensionality reduction technique works better before doing something like this, I think. I was thinking UMAP and TSNE personally.
Very likely, Isomath, it's relatively easy and is as one parameter that, at least from the climate perspective, is very easy to understand. And so for us, and really for Fabrizio, that was an obvious choice, because again, some of those reductions that are nonlinear have multiple parameters that sometimes are hard to at least interpret from. As far as this go, Saibal is a computer scientist who likes, and this is for a very pie in the sky kind of proposal. And so we had to go pie in the sky. And so this is what we put together as pie in the sky idea. And I don't know if we will ever, get to do it, but we do want to. We have not defined all the details. I mean, this is yes, so we should talk. I totally agree. We could not write something too simple, because part of the proposal was also to develop something complicated on the AI side. So we have to make it complicated.
Alistair?
Hi, Annalisa. I haven't really seen anything like this before, so I'm kind of wowed right now. But I have a question about the inputs and the issue of the slow manifold. So I think I heard you say you're using daily data.
Yes.
Is that right? So when you said the word slow manifold to me, I was thinking you'd be wanting to look at monthly data, and also variables which don't have fast signals in them, like waves. So maybe 500 millibar height and other variables. And so I was kind of curious why you needed daily, and why you chose these particular variables when there might have been other things which had more directly linked to the slow dynamics.
Yes. So, well, why why daily? Because it's not obvious that you need a lot of data to be sure that the average dimension you get out and the distribution is sensible. And I think we should try to do it with monthly, but the problem is, so you do want to get to something which is quite well defined here.
But there are samples which have monthly data versus one with daily data. So you have that data sets with the monthlies in different forms.
Yes. We started this work when there was not a lot of CIM6 out to begin with. We were looking for daily output. This was what was available. And I was in Italy and everybody was just easier. Let's go. It's the best model ever. And so we had to try. And we started with the high resolution, and we, Fabrizio wanted to play with it and see where we could go with those ideas. And they have been applied to weather mostly so far for extreme, this kind of quantities, the metrics. And so we were trying to see where we could go. So in a way, it's, yes.
Should we take one last question? I know that this is the last talk.
It's fine. It's an interesting question, though.
Go ahead.
No, it's a simple one. It's actually related to the question. This is actually lecture for the viewers online. Related to the question of extreme you just mentioned. So I guess one view that people tend to take from a dynamical system perspective is you would see your system is evolving in an attractor most of the time, and it's your background stuff, right? That's the stuff that you're isomapping. And then you would see the extremes as large excursions from the attractor. They don't live on the manifold themselves. So presumably when you do the dimensionality reduction, the extremes are kind of washed out. And I guess you need to account for them somehow. It looks like in the data set you're using, the points are kind of compact in space, I guess.
Well, the extreme in the analysis are those, right?
Right.
Which are missing completely.
And you still have a lot of data, a lot of extreme data.
Yeah.
That's not bad,
yeah. Yeah. This is exactly a piece of the manifold that, if you see it in 3D, it's completely non-explored by the models.
So what are your thoughts on fixing it?
What is?
What are your thoughts on fixing it, like putting the extreme dimensionality?
I don't know yet. I will have to try. But yes, I think that the reason that I will not trust any kind of projection of what ENSO is going to do in the future here, it's obvious. There is no way. If this is what I want to know, how those are going to be in the future, because those are the big events, right? And this is the one that you want to know. Are going to be more extreme and more often or not? Well, clearly the answer is we cannot use those models to answer that. That's it.
Right. Maybe wasn't a useful question after all. Thanks.
Cool. Well, I guess that concludes the talks.
Yes.